Switch to the cloud. Welcome everyone to this week's HoloTube seminar. We are very grateful that Wilke agreed to give a talk on attractors and what attracts to them. Please go ahead.
Well, thanks very much for the invitation and all of you for attending. Yeah, so I'll be talking about what attracts to attractors, far from equilibrium to hydrodynamics. So this is actually already a little bit of a while ago, although I joined this project after this July version, and I only kind of added a small part to this, the ADS-CFT part, basically, to this paper, collaboration with Alexei, Kurkula, Urs Wiedemann, and Bin Wu, all here at CERN. Well, I'll also try to give a bit of an introduction and some kind of state-of-the-art overview, as I was asked, and it's supposed to be very interactive, so please ask questions anytime if things are not clear, and I also encourage to keep on your video if to see a little bit if people are still following, and yeah, please stop me anytime. To start as an introduction, so also a few years ago, we wrote this review on heavy ion collisions and basically formation of quark-gluon plasma. And this talk will be basically motivated by that. So this attractors, really the beyond hydrodynamics to some extent, far from equilibrium dynamics of a heavy ion collisions. At least that's one of the prominent motivations. And so we actually listed like 10 questions in heavy ion collisions, and perhaps what we felt was the most urgent are these first two. And the first one is really, I think, what I've been motivated in my whole career also, like how does quark-gluon plasma form and hydrodynamize within one Fermi over C? So this is kind of the paradigm of heavy ion collisions, is that you have this collision, and the first, well, it's a collision of many partons or maybe strongly coupled fields. And after a while, it becomes applicable by hydrodynamics. And we actually in this field we coined this new term hydrodynamize to also emphasize that it's not a thermal system. So it's in particular not isotropic because there are large gradients and you would have viscous corrections. And this attractor business, I think we can show that we can go considerably beyond kind of these viscous corrections, like second order or maybe in some sense infinite order hydrodynamics. And yeah, I think this. So what also will be a topic in this talk is that there's kind of non-perturbative and perturbative calculations of this kind of far from equilibrium dynamics. So I'll show you a little bit of both and kind of the differences and actually also similarities. So this is kind of the holographic or the perturbative way of computing these collisions. And in particular relevant, and maybe not so much for this talk, but what's really an open question in heavy ion collisions is the limits of applicability to hydrodynamics. So it was actually a real surprise when the first proton-led collisions were done, that you see very similar hydrodynamic-like signals. And if you actually run your hydrodynamic simulation, you'll see mostly the same type of signals, and you can actually predict more or less what the experiment finds, like in the anisotropic flow coefficients. I don't want to go into details, but it's very surprising to some extent that even in a system with maybe only 10, 20 particles per unit rapidity, you see this kind of hydrodynamic picture working. So previously the idea was if you don't have so many particles, they don't scatter so much because it's kind of weakly coupled at very high energies. And well, then you wouldn't see these kind of correlations. So you would expect this hydrodynamic to smoothly turn off. But now even last year, 2 years ago, in high multiplicity proton-proton collisions, you see the same kind of signals. So in some sense, experimentally, at least, we have not found the limit where hydrodynamics is not applicable anymore. And then I kind of stress that you need really this hydrodynamics again with viscous correction. So in that sense, it is very relevant, like the study what we do, like order by order. Yeah, so they say that you don't that all these kind of small differences, they will have a larger effect in these very small systems. Yeah, so that's kind of the motivations from this heavy ion point of view. So okay, so to summarize that a little bit, is this like when is hydrodynamics? It's kind of what kind of hydrodynamics? So I already kind of said first order viscous, but second order is important, and actually it's attractor you can kind of think as an infinite order hydrodynamics, and it also will depend on kind of the position on the transverse plane, and that kind of can also be important, but I won't say much about that in this talk. And okay, part of the motivation to study this far from equilibrium dynamics is you have some kind of collision, far from equilibrium, and then you start your hydrodynamic simulation, and that's kind of what's kind of quite well understood, how you do this hydrodynamic evolution. But the hydrodynamics needs initial conditions, and so the initial conditions are both the energy density profile, and well, maybe this talk will not say much about that, because well, you have like some collisions, so you have kind of an overlap region, but then there will be fluctuations in that, and so that's kind of the way you deposit your initial energy density. But once you have this kind of energy density, this will evolve over time and also depend on the position, and you kind of need this kind of initial stage model to kind of evolve this forward, this in kind of this far from equilibrium region, and then you need your initial condition for your energy density and fluid velocity profile. And what I think is important for the field is that this kind of attractor story, well, people often said, and I'll summarize a little bit like how this argument comes around, is that you have this memory loss due to an attractor. So in some sense, you have your initial conditions, which can be very far from equilibrium, but very quickly you go to the attractor, and then everything is kind of hydrodynamics. And well, since it doesn't matter what initial conditions you start, you always go to this attractor. You can say there is this kind of memory loss. And I'll kind of put a little bit of some caveats in this talk. And well, first of all, because dynamics is not necessarily on the attractor, I'll show some examples in particular in ADS-CFD. And well, and even if you are on the attractor, then you still have like this kind of lot of 3+1 dimensional dynamics, which in this talk will be, there's not much work on like boost invariant, non-boost invariant, and transfers in homogeneous attractors. It's very hard to kind of model that in, for instance, ADS-CFD. Well, okay, I decided to do the talk a little bit to kind of show you kind of the state of the art of attractors, and then kind of go into a few examples in much more detail. Like that was kind of this paper what we did. But this paper by Giacolone, Masliauskas, and Schlichting, they summarize very nicely the state of the art of attractors and how this actually influences the quark-gluon plasma and heavy ion collisions. So I'll show you also a little bit of what they think is experimental result on the next slide. So I wanted to kind of go a little bit slowly here and try to kind of explain this curve, since it is kind of, in some sense, the main result in the whole field of attractors, at least in my point of view. So first of all, I already said, like, almost all these works, I mean, there has been some trials to go to kind of non-homogeneous situations in the transverse plane, but that has always been very hard. So I will not say, the last slide is kind of some scope of that, but I will not say much about that. So everything is completely homogeneous in the transverse plane, and it's boost invariant in longitudinal direction. So if you have this collision, then the temperature profile and the velocity profile, they all don't depend on the rapidity. So if you boost it, if you know everything at mid rapidity, at the time axis, then you can boost it and you can find the same solution at any other place in rapidity. So all these kind of constant proper time curves, they have the same temperature. If the fluid velocity by definition is 0 by symmetry at mid rapidity, and the fluid velocity at y=1 is exactly this velocity. So that's of course what it means to be boost invariant, and that greatly simplifies the problem, because that means just you effectively have 0+1 dimensional dynamics. So everything is fixed in the transverse plane and in the longitudinal axis. It's still non-trivial because of this expansion, so everything cools down. And for instance, if you have free streaming, your energy density will go down like 1 over time, basically because if you double the time, your volume also doubles. So it's just particles, they just fly out in free streaming. In hydrodynamics here, so this is kind of the late time solution in this case, it doesn't go like 1 over t, but it goes like 1 over t to the -4/3, where t is then proper time. So it's maybe better, I should say tall. And this is really because of the work done. So at very late times, the plasma will isotropize. So you will have a longitudinal pressure, which is the energy density over 3. And this 1 over 3 actually means that there is like a longitudinal pressure pushing wanting the plasma to expand. Yeah, this causes this power 1 over 12 to the power -4/3 by the work done. For conformal theory, I should say, but it's also something we usually assume. So, okay, so this is this late time result. And what's plotted here then over here is like the the energy density as a function of time divided by this late time hydrodynamic result. So by construction, all these things, they should go to 1, which indeed do. This is as a function of, well, it's not quite time. It's actually dimensionless time. It's proper time times the effective temperature, which is actually the energy density to the power 1/4 with some kind of a proportionality constant. And then it's also rescaled by eta over s. And it's rescaled by eta over s in such a way that, so for different theories, for instance, for strong coupling holography, most of you will know that the eta over s is 1/4 pi. But for weak coupling, the eta over s is much larger, goes to infinity if the coupling goes to 0, which also means that it takes much longer, in particular, to go to this hydrodynamic result. And it also means that the corrections to hydrodynamics for the energy density as a function of time will also be larger. So by rescaling this eta over s in this way, you kind of rescale the corrections and the time. It exactly cancels, and this curve is then universal and for all these theories. So here they show this kind of the energy density as a function of time, and the attractor for all these theories. So QCD kinetic theory, Boltzmann and relaxation time approximation. So it's a little bit simpler because it doesn't. QCD is kind of the full theory. Young-Mills kinetic theory, which is then a simpler version also from QCD kinetic theory, and ADS-CFT I'll say much more about. So yeah, so this is kind of okay. So to realize is that this energy density first, usually, actually always, probably also for ADS-CFT, goes like free streaming. So that's what these are these 3 lines, and then the energy density kind of decreases faster. There's this factor here due to this work done, and all these theories they look fairly similar, but I kind of want to stress that it depends crucially on this rescaling of eta over s, and that there are some differences between these theories, but that one of the points of this interesting paper is that these differences are really very minor, so like order 10–20%. Then kind of what can you do with this? So this attractor determines the pressure. If you know the energy density is a function of time in this simple setup, you can actually compute the pressure. It's just a derivative. So the pressure would be 0 in free streaming and would be 1/3 in units of the energy density at late times. And this can also be used with some kind of algebra to compute the entropy density at late times. And so they kind of derive this relatively nice formula where you have this kind of proportionality constancy, which is listed over here. So it's depending on the theory, which is the factor between these different curves. And then in particular, so it kind of tells you that if you know the initial energy density and you know eta over s, then by just following this curve, so you know at which point on the curve you are, you can kind of imagine, since at late times the entropy density, the total entropy in ideal hydrodynamics at late times is conserved because it's ideal hydrodynamics, which in particular means that because the volume still expands, that the entropy density goes like 1/tall. So the point of this formula is, to derive, that takes a little bit of algebra, but if you know that you're somewhere here on this curve, like the energy density will go like 1/tau because it's free streaming, then by just looking at these curves, you can go to infinity, and then you know also, where you end up at infinity. So, and then in infinity, it's quite easy to convert this energy density at infinity to the entropy density at infinity. So kind of the essential bit to get to this formula is to realize, okay, that there's a one-to-one mapping. Once you know where you are, which theory you have, so which C infinity constant you have, then you know what's the final entropy you'll find. And then in heavy ion collisions, it's very well known that since the final entropy, if you convert it with some kind of Cooper-Frye prescription to particles, then this uniquely fixes the number of charged particles. So it's basically the entropy density times the area. So it's the density times there's the total entropy, and then there's a factor, then the number of charged particles per entropy, which is usually taken to be 7.5. Yeah, I think this is a good point. So kind of maybe take some questions here, or was this very clear?
Sorry, I have a question. In the equation for the entropy density, how do the units work?
Exactly. So that's thanks for the question. So So indeed, so actually, so most of this, so of course the constants, they're not fixed by dimensional analysis, but for instance, what will be essential on the next slide is that it goes like energy density times to 2/3, and this is then fixed by dimensional analysis. So its entropy density is units. It's in the transverse plane, so it's units 1/length squared times time, so it's 1/length, and energy density, of course, has one extra. Well, the energy itself has units 1/length, so this is 1/length cubed times t, so it's 1/L squared, and that's why there's this 2/3 to compensate for that. And then well, these are the degrees of freedom of the theory. So this is dimensionless. Eta/S is also dimensionless, and this constant is also dimensionless. So to kind of, because energy density is 1/length to the fourth, and entropy density is 1/length cubed, you kind of need to have this 2/3 here.
Okay, thank you.
But that is indeed very important. Okay, so what they then did, and I think it's kind of nice to kind of also make a relatively direct connection to experiment, is that since you kind of always have to follow this curve, it kind of means that if you know the initial energy density, you know the final entropy density, and then you know the final number of particles. And this they kind of show in this kind of plot, and they did it. They computed this kind of final number of particles as a function of centrality in well, this is kind of a simple Monte Carlo Glauber model for the initial and the profile of the initial energy density as the transverse plane, and then they integrated the transverse area. So that's something which is somewhat different. But how to map then that energy density to the entropy density, they then did using this formula where this power of the 2/3 is very essential. So they did it actually in two ways. So it's kind of the canonical way, or the kind of what they call without pre-equilibrium way. So this is the blue dash line, but it's very much based on kind of saturation or color glass condensate dynamics. I don't want to really go into. It's kind of a particular model, but you need some kind of model to kind of have the initial energy density. And in that case, there is kind of, if you have this collision of two nuclei, you have like some parton density of the left moving nucleus and the right moving nucleus. And in this case, you take the saturation scale of the saturation scale will be determined by the energy density of the nucleus, basically, or the thickness function. That's why it's called T. And well, if you have like at some point in the transverse plane, either the left one or the right one has the most energy, basically, or participants density, and you take the smallest one, and that will then give you the gluon density. And in the canonical color glass condensate way, it doesn't depend on the other one, because it kind of saturates. And that kind of gluon density, if you don't include any dynamics, gives you directly the number of the entropy, and it gives you directly the number of n charge. So that's kind of plotted as this blue curve. I actually don't want to really go into detail, but here, because that's not what it's about, but if you assume that, so you have the number of gluons, but these gluons, they also have a certain number of energy, and the energy does depend on the saturation scale of the highest QS nucleus. So if the left or right, so this is not left or right, it's really the lowest and the highest thickness function as a function of the transverse plane. So it's kind of, so the energy density is not necessarily the same, and it gives a different formula, basically. And then what they kind of realize is that it's partly by dimensional analysis, to be honest, but it's, if you take then this energy density to the power 2/3 and you integrate that, then you get some entropy, gives you the number of charged particles, and this gives you this green line, and it actually fits perfectly with the data. So that, I think, is very nice, so that they kind of more or less from this attractor kind of could get a very nice view on this kind of formula and why this 2/3 came here. Also, because this 2/3 actually kind of relies on in this very initial time free streaming, so that the energy density times time is constant at a very initial time. So it could have been a little bit different, I suppose, if you would have different initial time scaling. And okay, so this worked very well. It's not only the attractor that goes in, it's mostly this power 2/3, and it's also this model of the initial energy density, which would, I think, look different, for instance, in some kind of more strongly coupled model. But still it fits the data very nicely, this green curve for all kinds of systems like xenon, uranium, gold. It doesn't really matter what you collide. And if you're more practical, then you can also turn it the other way around. So once you then know the final entropy density and you can estimate and the final number of particles, and well, you kind of know for QCD what are the number of effective degrees of freedom. And as I said, like the entropy per particle is about 7.5. You can really kind of know, we know more or less what's the initial area of the collision. This attractor you can estimate. Then as a function of this initial time, you can actually estimate the energy density, and then it turns out to be 270 GeV per cubic centimeter, which is it's really enormous. Like a proton has about maybe half a GeV per cubic centimeter, or even less. So it's like more than 1,000 times the QCD crossover density. So this is kind of, it gives this relatively sophisticated formula for the initial energy density. More questions about this particular calculation or the introduction? Okay, then I want to kind of go a little bit. So how to actually compute these attractors? What were the initial findings, and then go a little bit to what we found last year. So I think the first paper was really this paper by Michal and Michal. Just kind of took the plot more or less from that. Took the plot from that paper, where you see in a somewhat different, more complicated way, same as the previous plot. Here they plot F, which is, yeah, it's a little bit awkward. They could have just plotted PL over E, which is the longitudinal the pressure, which is the kind of the thing you're always interested in, but they had like a relatively complicated formula, and that's what they show. But here I show, for instance, that it's a linear transformation. So this is PL equals 0, and this is PL E over 3. So this is ideal hydrodynamics, and PL equals 0 is really the free streaming case. And what you see is that no matter the initial conditions, in this case, it's just Israel-Stewart evolution, all these curves rather rapidly go to this kind of universal attractor curve. So So basically in this talk, we'll consider 3 types of theories or attractors. The first one is kind of the hydrodynamic case. So this is kind of this original one, the Israel-Stewart hydrodynamics. The second one is the Boltzmann equation, kinetic theory, so in the relaxation time approximation, and then later on I'll go to ADS-CFT. If you do this hydrodynamic case, so in this case I very clearly see this attractor, you just look at the Israel-Stewart equations, and you kind of, so these equations, that depend on the anisotropy and the energy density. So once you give an initial energy density and initial anisotropy, you can integrate these equations, and that's how you get all these kind of curves. So all these curves, they start at a different initial time with a different anisotropy, and you get this family of curves, and you see that they very clearly go to this kind of universal case. There is actually what I, since this talk is about attractors, I want to specify a little bit of a subtlety here when people, at least more mathematically inclined people, are talking about attractors, because they always ask, like, how is the attractor defined? And from this figure, you kind of see it very clearly. You see this kind of pink curve, and all these curves go towards the pink curve. But to some extent, that's not completely fair, because if you take any one of these curves, then all the other curves, they also shrink to that curve. And this, in that sense, so it's not quite true that the attractor is the curve where all the other curves go to, because the whole band of curves goes towards the hydrodynamic curve at late times. So it's only in this particular case that there is actually a very sensible definition of the attractor, because all these curves, they actually, if you let them go backwards in time, they diverge, except for the pink one. So in this case, the pink one is really the curve that has a finite value when you let t goes to 0, which is a little bit of a, mathematically you would define it maybe a little bit differently, but it's kind of important to realize that there is a bit of a subtlety in this definition, and that I think in this case it's very clear, also visually, but I think that's mostly it. So it is kind of clear what you mean here, but it's not exactly the mathematical definition. Very similar thing happens for this kinetic theory. So you also have like, you have some kind of, the distribution function. Yeah, maybe just go ahead and ask a question. I think it's a good idea.
Hey, Wilke. So thank you all for the explanation. So my question would be, how do you actually get the curve mathematically? So not only the definition of the attractor, but how do you compute, for instance, the purple curve? Probably not by doing, I don't know, 1,000 simulations with different random initial conditions, and then you get the curve. So how do you get it from the equations?
So in this case, okay, let's see if I remember. So in ADS-50, it's definitely the latter part that you say. You just run many of them and then you try to get as close as possible. It's kind of, in some sense, visual. And then for Boltzmann equation, I also looked at that carefully. Let's see if I remember the answer. Yeah, because I think there is a particular, so you start with some initial time and some initial anisotropy, and then I think you can show that there is only, if you start, you do a small time expansion. So you cannot get the whole curve analytically, that I'm very sure, but you can get like the initial condition as a small time expansion, and then run your MD solve to get the curve. So that's how it's done. And actually, to some extent, any initial value at t equals 0 that does not diverge, because all the other ones they diverge, will do. So it's in that sense not very difficult, but you cannot solve this equation analytically.
Okay, thank you.
Yeah, so as I was saying, so very similar for the Boltzmann equation. Actually, you also have like some distribution function f, and you kind of have in the relaxation time approximation, you kind of solve all these initial conditions, which all have different initial anisotropies, and then it turns out they also all relax within a time of 1 over the relaxation time to this kind of universal curve. ADS-50 is a little bit more difficult, and I'll say more about it in the next slide, I think, or a little bit later to kind of, well, yeah, okay. So this then goes to kind of what we did ourselves. Actually, it's relatively similar follow-up to this work by Romachka, where we're also that looking a little, especially in this kind of early time behavior of the kinetic theory and the hydro figure more carefully. And what we noticed is that, so this now, I mean, well, also in the previous slide, but you have to be careful that this is on a log scale. So this is really the anisotropy as a function of time. And what we tried is you start with initial condition some anisotropy and at some initial time. And it's relatively easy to understand actually, but you see that all these initial conditions within basically a time scale that's on this plot, it's the same, right? But it's of course different real time because it's a log scale. So it's the time scale itself, how you go to this kind of relatively clearly this black line, so this attracting curve, is in this case really set by the initial time itself. So if you start very early, then within a time 2 times this initial times, or 3 times maybe, you go to this attracting curve. And this is actually quite easy to understand, because if you look, we're living in this boost invariant system, and this is a relaxation time approximation. So you kind of have kinetic theory, so your particles scatter, but they don't scatter all that often. They scatter in a time scale of 1 over the temperature, perhaps, or the energy density to the power 1/4. That's the typical time scale they scatter. So if you look at very early times, they basically don't scatter at all. So this very early time is just given by basically by free streaming the particles. And so you have to realize that if you have like a perfect boost invariant system and you have free streaming particles, so they don't scatter at all, then they're all produced at this point. And then, well, the particles, they move, of course, but the particles by definition, which end up at mid rapidity here at c equals 0, they have a velocity which is 0, because if the velocity would not be 0, then it would be at another rapidity. So in that sense, if you put a plate here, for instance, there is no longitudinal pressure. So basically, if you have a free streaming, perfect, how do you say, perfect boost invariant system, then you don't have any longitudinal pressure. What you do in these kind of initial conditions, you say, well, yeah, but the initial condition is not perfectly point-like. And we actually start at a somewhat later time, say t equals 0.01 or something like that. And in this t equals 0.01, we don't start with PL equals 0. We start with an isotropic case, which is like, it's a sensible thing to do. The velocities are basically random or isotropic. So then there are actually particles which go this, and the particles go like that. Because it's a finite size system and particles are isotropic. But then a little bit later on, these particles, they fly out, and very quickly on, you at mid rapidity, you select only the particles which had zero longitudinal velocity. So basically how you interpret this curve is that you have this kind of free flying particles, and by looking at just the pressure at mid rapidity, then there's no interactions. You have to have like this free streaming pressure, which is PL equals 0. After a while, though, then the particles do have these interactions. They're of course important, and it will actually try to isotropize. And after quite a while, then also the plasma expands, but doesn't expand so fast anymore, right? Because the volume is already quite big. So there's actually time to locally equilibrate, and this is actually exactly given also by the by this universal curve then, because it doesn't depend anymore on the initial conditions, and well, it goes to isotropy, and the leading one correction tells you something about the viscosity, for instance. So this is how this attractor actually works in kinetic theory. I think we understand both this small early time and late time behavior quite well. Questions about that? Yeah, and also to come back actually a little bit to Kyril's question, how you compute this. So as I said, so you cannot really get this attractor analytically, but what we could do is like this early time expansion. So you kind of have in relaxation time approximation, you can like kinetic theory, just scattering of particle, you can do like as a function of time, like for instance, the single hit approximation, which is you assume that every particle hits once. And then you do the double hit, three, etc. So this gives you kind of an order by order expansion in approximation of your true pressure as a function of time. You can also expand backwards. It's kind of the eta over S expansion, and then the green one is actually Paddy approximant of these two expansions, and then the black one is then the numerical result. So you can, if you're running to the Paddy approximant, then you can actually get an analytic formula which is very accurate. It's kind of how you see this. Also note actually that this log scale here is a little bit how do you say, it can be a little bit confusing, because this black curve here, it's exactly the same black curve as this one. It's just not on a log scale. So the pressure anisotropy does kind of grow linearly with time at initial time in units of 1 over the relaxation time. More questions about kinetic theory or the relaxation time approximation? Well, then, I want to go on to ADS-CFT, and of course, especially since this is the HoloTube seminar. So then we wanted to see, of course, how this, I guess we already knew a little bit that it was different in ADS-CFT, but we wanted to study this more carefully in more or less exactly the same setup. So I came up with this kind of some relative. The point in ADS-CFT is that it's not only the initial anisotropy which matters as an initial condition. So we use this kind of numerical scheme, which most of you are very familiar with. It's like this Eddington-Finkelstein theory, and then you can solve your equation numerically. I don't want to go into any details, but I want to point out that you have an initial condition, which is this function b, which kind of is the anisotropy of the coordinates, and you need to specify it as a function of z, so the ADS coordinates, at an initial time. The near boundary behavior of this actually determines the stress tensor, and it does determine the initial anisotropy, and also the derivatives that near the boundary determine the time derivatives of this anisotropy, for instance. But okay, I reiterate that you cannot just specify the anisotropy. You really need to specify this whole function as a function of rho, the radial ADS radial coordinate at some time t0, and you need to specify the energy density, and that you can then scale out. So it's kind of a choice of units. So you want to kind of know how this attractor looks, and well, the thing to do is just to study a wide range of initial conditions. So that's basically these kind of two profiles I made up. By the near boundary expansion, it has to go like rho to the fourth. So this one is forced upon you by the ADS-CFT near boundary expansion. And then I just tried a plus b rho with a and b free parameters. And a second one, which is actually quite different. So it's also a plus b rho, but e to the power minus 40 rho, where rho equals 0 is the boundary. So if you take this e to the power minus 40 rho, then it very quickly goes to 0. So this profile is really focused very much close to the boundary, and that's why I call this UV profile. And this one is more or less constant if you don't take this rho to the fourth, which is forced upon you. This one stays, if rho equals order 1, then this stays fairly constant, depending on this coefficients A and B. So that's what I did. So there's kind of solid and dashed for this kind of IR and UV, and it various values of A and B. And well, this is just to show you that you get many curves, many evolutions. And I think I'll make it actually a little bit clearer in the next slide. Yeah, just to show you that we tried several initial longitudinal things and several derivatives, and they can even start very negative in the longitudinal pressure. But then in the end, they all go to this kind of universal black. The black line is viscous hydrodynamics, second order hydrodynamics, and the dashed line, the first order viscous hydrodynamics. So they all really go to second order hydrodynamics here, where there's still a significant difference between first and second order. So if you really want to describe this here with hydrodynamics, you kind of really need second order hydrodynamics. I'll say more about it. I just want to say that this is a little bit arbitrary, but in principle, you could get these kind of profiles from kind of shockwave collisions, for instance. That would be more like well-defined initial setup if you kind of believe that would be a proper description of heavy ion collisions, which you can doubt because it's not really in QCD. Okay, so in the paper, we kind of summarized this a little bit. So this is what I did as a more or less initial study. There's tried very many of them, but then wanted to put it like exactly the same thing we had in the kinetic theory. So we really we put kind of the same scale, different 5 different initial times, and all starting at isotropy, which is just somewhat arbitrary choice of your initial conditions. I mean, it doesn't have to be, there's a kind of choice. And I also gave them all the same derivatives. So this is kind of not the rho to the fourth, but the rho to the fifth term. And then I showed this kind of dashed and solid lines, which is again, these kind of UV and IR kind of different initial profiles. And it really looks like this. And I think that you can already see that kind of, so these UV profiles, these are these dashed ones. And the IR profiles, they fluctuate much wilder, and they also take longer to kind of go to the same curve. So for the black and the blue ones, you can argue they're already at the same curve here at like t equals 0.3 or 0.4 in units of 1 over the temperature. And what's also clear is that, especially for these IR ones, it really takes, no matter what's your initial time, it really takes a time of, in this case, order 1 in units of 1 over the temperature to kind of go on this universal curve. And for instance, if you start very, very late, you see that it immediately goes to this universal curve because it goes in the time 1 over the temperature, and on this log scale, the unit of 1 is very small here. So this is kind of how this is also consistent with this early time behavior. But it's kind of strikingly different from this kind of kinetic theory approach where you have this free streaming first, and it really goes very quickly, not in a time 1 over temperature, but in time 1 over the initial time. So it's parametrically different, and that's what we kind of wanted to point out in this paper. Questions about that? Well, then I wanted to say a little bit more about, okay, so this is kind of going to the attractor in ADS-CFT in this visual in this picture and the distinction between RTA. Yeah, just go ahead. You don't have to raise your hand.
I do want to, because I don't want to, to interrupt you too much. Question. So does it mean that you actually have several attractors? Or how
okay,
many?
Yeah, that's actually a very good question. I'll come back to that. Yeah, in the slide after this. Okay, well, first of all, okay, so indeed, this is question of what is the attractor, and are there more attractors? Like here, okay, so first of all, I think it's good to kind of revisit kind of how it goes exactly to hydrodynamics, or how it hydrodynamizes. And for this, we use this very nice paper by Michal, Yannick, and Wilke, which actually put their results also online, so you can actually just download and plot these curves. Very, very convenient. Where they show the pressure anisotropy. So what I just showed is function of time for hydrodynamics of kind of any order. I think they give it order 25, but I'm just showing for the first few orders. And for instance, like this is order 1 then, and then there's order 2 and order 3, 4, 5, 6, 7, etc. And as you maybe expect, you cannot use hydrodynamics at very early times because this is an asymptotic series. So the higher order you go, it starts to diverge actually earlier and earlier on. So this yellow one is actually order 12, so it starts to diverge earlier than the order 8. And actually, when we compare to what they say in their papers, I think that order 7, is the black line, is maybe the optimal order in some sense, because you kind of have to this interplay between being more accurate, because first order is not accurate enough, second order neither, but then there's also the divergence. And then I want to show these two plots together. So these gray lines you may recognize. So these are again all these ADS-CFT lines. I didn't dash them anymore, but I think maybe you recognize them. And I show all these hydrodynamic orders. So first order, second order, and then the 7th order, which I kind of argue is maybe the best one to some extent, but also diverges, order 30. And then, yeah, okay. So well, first of all, I think I already said that if you look at this around t = 1, you really need the second order hydro, and it goes to second order hydro. But what really interested me in particular in this result is that if you have these UV profiles, so these profiles which go to this line relatively fast, like even this relatively late one goes over here, then you really see it goes to this, not even the second one, which is the second one is this curve. You really need kind of the 7th order one here, right? Because it's they all agree and they don't agree with the second one. So I guess this was already kind of in words said in other papers that you kind of need to, that this attractor is really the resummation of all these kind of hydro modes. And well, I think if you look at this divergent series, it's quite easy to take this order 7th and just draw this curve basically to 0, and that's the resummation of your asymptotic series. And this is in fact what is done in this ADS-CFT work, because there the attractor goes to PL equals, well, so it goes to -1, which means the energy density goes like 1 over time. And that also means here, this ADS-CFT results here, that is the free streaming result, also means PL equals 0. And this is, yeah, so I think that this is definitely suggested by this kind of how you see these curves going to actually to 0 here. How to actually analytically show that this should go to 0, or how to compute analytically this curve, that's not clear. I think you really kind of have to look at all these curves and see what's the reasonable attractor, and then indeed it is this curve extrapolated to 0. And then yeah, okay, so similar question, like what is the definition, how do you actually compute it? And in the end we didn't kind of, well, in the paper we put the conclusion a little bit in 2 ways. So first of all, okay, you do see some kind of attracting behavior, but it's also clear that it's not the same like in the relaxation time approximation here. In T0, in the time T0, you're always on this curve. And then it's also quite clear what you mean by the attractor and how it is defined. So just a T0 to 0 limit, and you have the definition. Here it's kind of, I would kind of say that this is the attractor, like this order 7, and then extrapolate to 0, and because you see these UV profiles going there, but the IR profiles, they don't. And if you look at it on a log scale, you could even say, well, maybe this is for this particular profile, this looks like an attractor. They all kind of are very close here. That's kind of saying a bit of this answer to Kirill, like, are there more attractors? Well, maybe for this profile, this is an attractor, but I'm not a big fan of that interpretation. I would more say, okay, these UV profiles, they have non-hydrodynamic modes and hydrodynamic modes. The hydrodynamic modes to all orders form the attractor, and the non-hydrodynamic modes, in this case, they decay quite fast, not in the time scale, the initial time scale, but in a time scale, well, really like 1 over the temperature divided by 4 or something like that. So really quite fast. And that's, well, that's at least my interpretation of the attractor. Well, that I guess somewhat similar. So these are all these curves on linear time scale. Then you see, for instance, also that this the attractor of these IR profiles, it kind of looks like an attractor on a log scale. If you look at it on a linear scale, it's not really a second attractor. I think it's really kind of this curve here. So kind of the limit of these blue dashed lines that you can say is really maybe the attractor. Okay, to kind of summarize that, so well, I think I said many times that it depends on this time scale where you start in a relaxation time approximation. I think I tried to explain that this is the free streaming. That's really, I think we also understand that. You can actually do this expansion also in early times and get even analytically the Spade approximate of this kind of attractor. In strong coupling, actually, it's a little bit more complicated. So there's kind of this decay in the timescale of 1 over the temperature. And you also really see that that your initial dynamics, and that's kind of important also regarding this motivation of heavy ion collisions, really depends by your initial conditions. So both the initial time a little bit, but maybe it always takes some time, but also kind of how the profile exactly looks like. So this kind of what I quoted, UV profile converges faster. And the attractor itself then, so this final curves, they're really kind of still, so I also, well, I didn't say much about it, but they kind of, in this case, this is universal for any value, for instance, of the coupling or the shear viscosity. Once you rescale this with 1 over tau r, so the relaxation time. So there's kind of this natural time scale, and that determines both the viscosity and the relaxation time. And you could actually argue if this should also have been a 1 over tau r, but holography doesn't have really this time scale. It's really the temperature sets the relaxation time in some sense. So that's why here we plotted in total times the temperature. Well, then there's a little bit of a speculative slide, because of course I tried to think quite a lot about why there is this difference between holography and in particular kinetic theory, which is kind of a very well-defined approach for recoupling QCD, and then it looks so different. And well, I think the reason is a little bit in this profile here. So this profile B is really either in the UV or in the IR. And then you wonder, like, why does this IR profile thermalize so late in the time scale of 1 over the temperature? And I think within holography, we actually kind of understand this, because there is this function B, which is then non-trivial from the IR to the UV in holography. And actually, if you look at your equations, you can see that this IR, non-trivial IR profile has to take a time of 1 over the temperature to kind of reach the boundary. So it's kind of a causality argument. And at that time, it actually causes some kind of bump in the pressure anisotropy. And there is a bit of an alternative interpretation there, is that also if you have, like, from the horizon to the boundary, it takes a time 1 over the temperature. If you have some non-trivial profile there, that also means that there is a non-trivial 2-point function at this length scale. So there is kind of this non-trivial 2-point function. And then basically by causality, this means that you cannot, thermalize or hydrodynamize. It basically means that if you have a non-trivial profile in your 2-point function, then it has to have non-trivial dynamics later on, and you'll see the difference between these 2-point functions. So in that sense, I think we understand why it's inevitable that you have profiles like this, which take a time 1 over temperature to thermalize. If you then buy this argument, then it becomes surprising. Yeah, but what if I have a 2-point correlation much larger than 1 over the temperature? Shouldn't that also have an effect, but then a much larger time by causality, which is very sensible. But then the beautiful thing about holography is then if you try to do that, this correlation much larger than 1 over temperature, you need to put this correlation function behind the horizon of the black hole, and that then doesn't have any causal information. So basically, the statement is, if you just look at the 1-point function, for instance, you cannot probe behind the horizon. So you could try to put these correlations there, but they will never influence your 1-point function anymore. In some sense, holography forbids you to do thermal correlation much larger than 1 over the temperature, which of course in a field theory language is also quite intuitive. And that, I think, also explains a little bit of this puzzle, why these UV profiles, they seem to kind of go to this attractor much faster. And that would then be because this causality argument does not apply. They only have small scale correlations by construction, and that's why they can kind of hydrodynamize much faster. So this is kind of the relaxation in causality argument. It's a little bit also, well, of course you can always try to argue that there are 2 points of view about weak coupling, like relaxation time or holography, and very often they give actually relatively similar results, especially at late times. For instance, if you kind of this is kind of this very initial work, like ADS-CFT, doesn't look very different from QCD. It's just a slight difference in kind of the normalization of the energy density. And this, of course, relies very much on this rescaling of the eta over s. So everybody agrees if the theory is different, then the eta over s is different. But maybe that's the only difference, that ADS-CFT is just just the infinite coupling limit of the same theory and the same kind of mechanisms. They work in both theories. And then, of course, we thought it was very interesting that here it doesn't seem to be the case. There seems to be a real qualitative difference in how initial conditions, or how this memory loss of attractors functions in weakly coupled theories and strongly coupled theories. Because here it goes very fast, this memory loss, and everything is completely universal. And here it's not. But if you then think more about this argument about the two-point function, it kind of goes against a little bit that you say, like, okay, weakly coupled and strongly coupled theories are very different because of this reason. I might say maybe no, because in the holographic case, if you put this UV profile, you don't have much two-point functions only on very small length scales, but not on larger length scales. And in weak coupling, of course, we do the kinetic theory as a relaxation time approximation, which means you're just looking at the distribution function, the one-point function. And there is no, in the initial conditions, there simply is no two-point function put in. So it's very natural that you have to compare with this kind of UV kind of setup. So it may be that weak coupling and strong coupling is not altogether that different, because this causality argument should probably also apply weak coupling. It's just that if you do the Boltzmann equation, that you lose this kind of two-point higher point correlation function. So it might be more about initial conditions than actually weak versus strong coupling, and this difference between the attractor and the attractors themselves. Questions about that interpretation or those results? Okay, well, let's see. So this goes again back a little bit of extra information on kind of the relaxation time approximation. So this is kind of, because we have this kind of full kinetic theory code, we can actually go beyond the relaxation time approximations. And this is kind of important because, well, so you have like, well, in the Boltzmann equation, you have like different momentum, and they all have different modes. But since all the momenta and relaxation time approximation, they decay at the same time, the relaxation time, that's why it's called relaxation time approximation. It's somewhat trivial how this happens. So you might actually think that this works different in full-fledged Young-Mills kinetic theory. This is kind of also what's done in if you're more expert in kind of kinetic theory and quark-gluon plasma thermalization, also done this kind of bottom-up thermalization. But okay, so here you kind of see that all these kind of curves, they still, well, okay, so you kind of have this the difference between the energy density and the hydrodynamic energy density. They all follow kind of also this semi-universal time scale as a function of the coupling and 1 over the time. So to kind of show that this is not only relaxation time approximation, but it also in the full-fledged Young-Mills theory, kinetic theory, you get the same kind of attracting behavior. Lastly, I wanted to put this kind of, it's a bit of an advertisement. So yeah, so first of all, okay, so well, there's this memory loss argument, and then there's the initial conditions, and all of this was just in 0 + 1 dimensions. And in general, I think it's also very important to kind of see like how the fluid profile evolves, and how the expansion goes, and how this would go in heavy ion collision. So these 3 + 1 dimensional simulations, I think they're really needed. And in this case, yeah, so it's at least for this case, I think you can more or less see how things change. So you can kind of have this. We look at again the same curve actually. So the PL over epsilon as a function of time, for relaxation time for different sizes of systems, or no, the different positions. So this in the center, this is at the radius, and this is at 2 times the radius. If you have really finite size blob. And well, this is then as a function of the opacity parameter, which is dependent on the coupling strength. So this kind of sets the shear viscosity, for instance. And so this is a dimensionless ratio where the whole dynamics depends on. Okay, all again in this kind of relaxation time approximation or kinetic theory, they give the same results. So you see again this attractor kind of going for this is I think the infinitely big case, and then depending like how big your system is, so if this gamma hat is, so this is kind of the infinite case, so what we kind of the homogeneous case, what we discussed before. So if gamma hat is 8, so that's kind of a large opacity, so it's kind of, you can think about it as either a large system or large coupling strength. So it's kind of they're in, because of conformal symmetry, that you can think about it as being the same, or a large energy density. It's all because of conformal symmetry. And then you see indeed that at some point, so the system starts to kind of expand in the radial direction. And because of the radial expansion, the radial pressure also goes down, and which means in turn that the longitudinal pressure has to go up. So you can actually see that it starts to deviate faster at the sides of the collision, and more slowly at the center. And then it depends very much what you actually put in gamma hat, how these kind of evolutions kind of start to differ. So this, okay, so I said kind of in the beginning that's a bit of to me still an open problem, like how really the attractor, or if you want the infinite resummation of hydrodynamics, works in 3+1 dimensions, and I think that's true. But this, of course, is a full-fledged microscopic RTA simulation of a 3+1D profile, and it naturally does depend on the size of this 3D profile. And in that sense, you can kind of say that these things are kind of the attractors or of this kind of 3+1 dimensional dynamics. If you kind of, these are really the kind of corresponding curves. If you buy this kind of attractor. But then for different places and for different sizes. And but what I think is also natural, but I also really like to show this curve, is that it really depends on where you are and how big the system is. And this is only for this RTA kind of system. So I wouldn't say this is a complete solution to the attractor, but this kind of shows you how things will deviate if you have more 3+1 dimensional systems instead of just 2+1. Well, okay, I think I already said a lot, and I think probably time to stop. But then, well, so these kind of to reiterate these questions we had in the beginning, from when is hydrodynamics applicable? And then actually, if you kind of buy this attractor story, then there's a very different answer in the relaxation time approximation, which is like 1 over the, well, it should be just the 2 times the initial time, of course. And strong coupling will be 1 over the temperature. So this is, and what kind of hydrodynamics we need? Well, for the relaxation time approximation, I think the attractor is this curve, which is kind of shown, and it depends on tau r, but that's it. Strong coupling, you can kind of, well, in some sense, I would always say that, okay, you can have this attractor, which Paul Romaczka basically drew, or which I kind of pointed out, you can also draw, but maybe it doesn't really matter so much, because the initial conditions, they kind of mean that you don't start on this attractor anyway. It takes quite some time to be on the attractor. So if you only care about the things you know for sure, which is the things that don't depend on initial condition, then second order hydrodynamics is actually enough. Sometimes for this UV attractor, I think I argued that you maybe should use the 7th order hydrodynamics, although I think that's pushing things a little bit, and it was a very small difference. So what is the attractor strong coupling? Well, you could take this curve by Paul Romaczka, and I think it makes sense, but I think the second order hydrodynamic results actually enough, and things just take a while, like 1 over the temperature to go there. Yeah, and then there was this 3-dimensional kind of thing, which I showed in this slide. Things can depend on the position. So, okay, so the initial fluid profile at the time. So is there really this memory loss? And I think at strong coupling, the answer is a little bit in the negative. So actually the evolution depends on these higher point correlation functions. And so in some sense, the attractor, at least in my point of view, doesn't completely solve this initial state problem. You really need some extra knowledge. And in particular, if you have arbitrary initial conditions, like in this work, you don't fully solve your initial initial stage problem. And this is important. I mean, the longitudinal pressure, as I showed in this formula by Giacolone et al. It determines like the entropy. It determines it will have some more radial flow. If you have less longitudinal pressure, you have more transverse pressure. So it will have some influence on the experimental variables in heavy ion collisions. Yeah. Okay. So the initial conditions will influence the final distribution of energy, and I think okay. So for the relaxation time approximation, it is really lost, the initial conditions. But maybe, yeah, so we should actually look more carefully at this higher point correlation factors in weak coupling too. And I didn't really do that, but it's also a bit of an invitation of people working in that field. Yeah, so the attractor doesn't solve all your problems. It's part of the conclusion, and I'd like to stop there.
Thank you very much, Wilke. That was a very good overview and very interesting. Do we have questions? If nobody wants to start, then I can ask a question, which might be so slide 4 or 5. I think 4. This has to do with the initial free streaming.
Mm-hmm.
Yeah, you said that the ADS-CFT, this value of C infinity there, that agrees very well with this free streaming solution. So I was just wondering, since it's not entirely clear if free streaming is the best idea or the best way to model the very first times. So is like how much does this change in ADS-CFT if you change that initial condition?
Yeah, that's actually a very good question. Let's see. So I didn't actually try to kind of put it on the same curve, which we of course could have. So this is the energy density as a function of time versus as a function of time, and we put the longitudinal pressure. It's true that if this grows with this power, which I guess is actually e to the power tau over 1 over tau to the power 1/3 to get this. No, okay, yeah. Then you have free streaming, so it would have PL equals 0. So then we can go to the ADS-CFT results, and so then, for instance, here PL is slightly positive, so if it would be 0 and would be on this curve, then it would exactly agree. That's definitely true. Here PL is slightly positive, but in this UV profile it goes to 0 quite fast, like within 0.1. So the total work done by the system, because it's a relatively small time and a relatively small pressure excess, would be relatively small. So there would be some work done, which would mean that it goes up, the energy density goes down a little bit slower, right? Because it's because it's the energy that if you do work, you lose a little bit of energy. So basically you would start a little bit higher and then would go up slower. And then you would still go to this curve after that. And then in the end, everything is normalized as a late time value. So I think actually, so you would have some slightly different slope here initially, and it would have then a slightly higher C infinity value. But this slope, and that also comes back maybe a little bit to Carlos' question. So if the slope is different in the beginning, then the energy density as a function of time is not 1 over time. And then this E over T should also change. So there would be different power here as well. And then of time here would be different power of time. And then by dimensional analysis, there would be different 2/3 as well. Well, that was not exactly what you asked, right? Or?
Well, it is definitely part of the answer. I was just wondering, so it looks like by just changing the initial conditions a little bit on the ADS-CFT runs, then you could have a much faster relaxation towards the attractor.
Yeah. So that, okay. So there are 2 types of answers. Yeah, indeed. So what I kind of described was kind of this UV profile, which would go very fast to this attractor, and then you would have more or less the same story. But there is the different story, which could be, at least since we don't really know these initial conditions, and well, we don't know which of these curves are that reasonable. If it's this black curve, they start relatively early on with a relatively deformed profile, then you have a very negative longitudinal pressure for a long time. And that will have a significant effect. So that will have like and that lasts for a time of 1 over the temperature. So it really, well, this 4p/8/s is 1. So it really for this whole period, it would have a significantly different slope. So it could look something like this.
Mm-hmm.
Actually, probably, yeah, it actually a little bit similar to also what Paromachka plots here. It's a similar plot. So this is the time derivative of that plot. And these are all kind of valid initial conditions.
Mm-hmm. Okay, thank you. Are there more questions?
I have a question. So
Yeah.
you talked about these correlations that you give this nice argument about, well, if you have a correlation that's longer than the size of the system, so on and so on. I was wondering, you'd have to be behind the horizon. I was wondering if there's anything that we would want to probe behind the horizon that, yeah, that's basically my question. So is there anything we can learn by looking at these correlations that are longer than the box, say from the UV to the horizon? Because it seems like the story is really nice from the UV to the horizon, but what else is there?
Yeah, that's a very interesting question. So I think like from a practical point of view, like just the stress energy tensor and the 1-point function, it probably doesn't matter so much what's behind the horizon because it cannot reach you, right? But it's not completely determined. So basically, I think in Madrid in particular, they looked in entanglement entropy after quench. So this Faidia type of geometry, and well, if you go to very late times, in thermal case, and if you compute, for instance, entanglement entropy or 2-point functions, then these things they cannot probe behind the horizon. But in this Faidia case in particular, it's very nice analysis, and you can actually relatively easily go behind the horizon in some time scale that depends on the size of the region probed after the quench. So it doesn't only depend on 1 over the temperature, like in the 1-point function case, but then then you can actually probe. You can actually probe behind. Does depend on physics behind the horizon. And for instance, in our numerics, sometimes we cannot probe that because we only have the grid till the horizon. So you actually have to do a little bit more. So it is, it's possible.
Thank you.
Any more questions? Okay, so I just note that after stopping the recording, we have the possibility to stick around and chat a bit. But before that, thank you very much, Wilke, again.
Thank you.